Welcome everyone, thank you for being here. We're going to talk about bloom filters. And let's try to picture a situation where you're building a browser and you need to make sure that your users are safe, that they don't visit any malicious URLs. Well, you know you have a list of malicious URLs and you have gigabytes and gigabytes of them. How do you keep your users safe? So, the first alternative would be to issue a request to your server just before your browser makes the GET request. And that may seem like an okay option, but if you think of it, then you're going to realize that it's not very good because you're going to flood yourself with requests. Say, if everyone in the world suddenly starts using your browser, every time they make a request, your server is going to get hit, and you'll essentially be DDoSing yourself. So you need to come up with a different alternative. And as I hope you'll understand by the end of this talk, it's going to be bloom filters. So a little bit about myself. I like goofing around with my sister. We're always playing around, and she told me that bloom filters are an Instagram thing. So I get to put this picture here and do a bit of public shaming of her. I'm still a student. I'm taking a master's degree in University of Minho. I usually hang around with the student center, and we've did a bunch of conferences and talks together. These are some of those. I'm also a volunteer at the local Coder Dojo, and I'm a developer at Subvisual. We do web and mobile products, and we also organize MirrorConf, which is a conference for designers and front-end developers, and RubyConf, which is coming up in the end of this month. So if you want stickers, if you want discount codes, just come talk with us in the end of the talk, and we'll set you up. Okay, so what's a bloom filter? If you go to Wikipedia, you're going to find something like this, which may seem a bit complicated. So let's go with the simplest definition, which is this one: a funky array with hash functions that's supposed to be really, really small. And I like to reinforce the small thing. It's supposed to be tiny. And how do they work? Well, they do inclusion tests. So let's picture this situation. You have a box, an array, and you query it saying, do you have ABC in there? And the bloom filter is going to reply, I definitely do not. And here's the thing. It says definitely. So you now query it about XYZ. And the bloom filter is going to reply, yeah, I probably have. So what's the deal here? This is strange because you have 100% probability of something not being in the bloom filter, but you're not sure if something is inside the bloom filter. The use of this may not seem obvious, so let's go back to the previous situation where you're building a browser and you have your server with all the malicious URLs. A user comes in and he asks if he can visit pixels.camp. You're going to go to the server. So this is the unwanted situation. How do you fix this? How do you eliminate that connection there? You add in a bloom filter, and the bloom filter is going to ship within your browser. Every time someone makes a request, instead of going to the server, you're going to go to the bloom filter first. So when you ship it, you need to pre-fill it. Okay, so let's start by pre-filling the bloom filter. We're going to go through all the URLs in our gigabytes of our database, and we're just going to add it. So suppose we're adding totallynotfake.com. Internally, what the bloom filter is going to do is it's going to hash it. And this is not a regular hash in the way that you're not going to get a new string or a checksum or whatever. You're going to get indexes of the array. So you're going to get 3 indexes, and the array is set to 0. The corresponding indexes will then be set to 1, and we just marked it in the picture. Moving along, we're going to hash the next URL, which is clickformoney.com. So we added 2 new indexes, and the third one was already filled, so we're not going to mark it. Essentially, we'd be just putting 1 where there was already a 1 in memory. So we have this bloom filter now with 2 URLs. Suppose this is the final version of the bloom filter, and we've shipped this with our browser. So now this is on the client side, and the user comes in and asks to visit pixels.camp. What we're going to do is hash pixels.camp and check the corresponding indexes. Even though 2 of them are set to 1, 1 of them isn't. So we are definitely sure that we never hashed pixels.camp to our bloom filter. And we can go ahead and say, yes, go ahead and visit because it's not in the Bloom filter, so it's not a malicious URL. On the other hand, if we do the same for github.com, we're going to hash github.com and notice that we had 3 indexes set to 1. And this is going to be a false positive because we know that github.com was never in our Bloom filter. But if we follow the Bloom filter's advice, we're going to tell the user, no, you can't visit github.com. It's really spammy. Don't do it. So how do we act in this case? Well, we go back to our previous scenario. Because the issue before was that we were DDoSing ourselves with all the requests from the internet, but now it's just an occasional request. False positives are not a common thing in Bloom filters. They're pretty rare, so it's okay to do that verification when we get a positive answer from the Bloom filter. So now we go to our server, and we're going to check and tell our user, yeah, you're good to go. So this happens because a Bloom filter is a probabilistic data structure. We either get possibly in set or definitely not in set. Since we have this probabilistic nature within our Bloom filter, what's the advantage? Well, it's all about space efficiency because we can fit in gigabytes of data into just a tiny array, and we can get a megabyte of it. It's pretty okay to assume that. Or as Justin Timberlake would put it, just drop the big. Anyway, what I want to consider now. So Bloom filters do inclusion testing. We've seen that. And they turn big data into tiny data. However, we must be careful because they also turn false into true. So we need to set a requirement for our applications, which is they must allow false positives. You need to have a fallback scenario. OK, so we're going to dive into Bloom filters now, like the actual implementation. And I'm going to show some code. It's in Ruby. If you feel like you're not getting it, just go ahead and tell me. We can go through really easily. Just be OK with that. OK, so we're going to start with a really small Bloom filter, a simple one, the most simple implementation we can get, which is we're going to code the malicious URL filter, and we're going to use a native hash. This is a Ruby hash. You get dictionaries in Python. You get maps in Java, objects in JavaScript. It's your choice. We're just using a native version. So how do we add something to the Bloom filter? We just go in, use the native function, and we set that value to true. And how do we test it? We simply retrieve that same value from the hash. And this has a great upside, which is we're using hashes, so we have instant access. And that's a good thing. It's going to be fast. However, we're saving key value tuples. Instead of just saving the URLs, we're saving the URL, the data structure, that extra bit, saying it's true, or it may be a byte, depending on the language. So essentially, we're saving a lot more data than what we wanted. And it's going to get really huge if you have gigabytes of data. So the solution is going to be to fall back to bit arrays. And this is the new constructor, the new method. This may seem like much, but we're only creating a new bit array with a given size. That's the default value. And we're going to instantiate a hash function. Like we're saving the seed, so every time we run the add function or the test function, the same URLs get the same indexes. So it doesn't change between calls, just using the same seed over and over again. And we're going to save the size. Moving along to our hash function, we're simply going to hash. You can forget the first bit. It's simply running that special hash. And then we're going to do the modulus operator. This modulus operator is really important because the first bit of that operation, getting the hash, may give you huge values. You can be getting huge integers. And we want to restrict that value to the index of our array. Say if we have a 100-bit array and we get 150, using the modulus operator is going to map to the 50 index. So we're guaranteed that we're going to not go out of bounds. We're not going to get an exception, segmentation fault, wherever. We're just going to put it inside the actual array. So we know how to hash. We can simply retrieve the index from the hash function, and then we can set the corresponding bit to 1. And testing is doing pretty much the same thing, except we're verifying that it's indeed 1. And right now, we still have instant access, which is good. And we have space efficiency, which is even better. But this has a small problem. And this might be tricky to get. If anyone has any guess right now, I'd really like if you just jumped in and try to say what's the issue with this implementation. Okay, so it's tricky, and you would only get it if you ran the Bloom filter through benchmarks over and over again, which is you're using a small universe, like you're mapping values to an array. So the range of possible values is going to be really small, and it's going to be smaller than your hash, which is going to result in more and more collisions. So collisions are a bad thing. You're going to end up with a lot of false positives. And the solution for this would be to add more hashes. It's really counterintuitive. How do we solve collisions? Adding more hashes. Wouldn't we get more collisions? But you can think of it like this. If it's really unlikely that two strings using the same hash function give the same index, two strings will probably not give the same set of values if we hash it once and then twice and then 3 times. Let's say you pass it through an MD5 and you get an index 1, and another string also gives you 1. So if you pass the first string through another hash function and the second string through that same hash function, you're probably going to get, say, 1 and 3 on the first string, and 1 and 5 in the second. So 1 and 3 versus 1 and 5 is not a collision. It's just probability. Okay, so moving along, this is going to be the new version. And I've added that, which is the number of iterations. We have 2 options. Either we had different hashes to be sure we attain different indexes, or we use the same hash function multiple times with different seeds. So I'm going to need to save those different seeds. And there's a seed function, which in Ruby is going to be something like this. We are just getting a random number n times. So if you're familiar with JavaScript, you're probably going to understand this version better using the map function. We're simply getting a list of random values to use as our seeds. Okay, so we save the seeds in a list, in a variable, and now we need to update our hash function. Our hash function must now receive the seed, and I actually changed the hash function just because this one explicitly receives the seed. I can just pass it along when I'm calling the hash function. So we get a hash value using a string, using a seed, and then we're using that same modulus trick. So this is going to give us 1 index, but we need several indexes, 1 for each seed. So there's that function. We're going to run the indices off for a given URL, and that's simply going to loop through the list of seeds, and for each one, it's going to retrieve the hash. So indices of is going to give us the corresponding indexes of the array. Now, to add, we're simply going to loop through all of those indices, and we're going to set the corresponding bit to 1. Testing is going to be a little more complicated because we need to test several times. We need to test the whole range. So if I get 1, 1, and 0, it's a false. But if I get all ones, it's true. And that's given in Ruby by the array.all function, which just checks if all of the bits have that same condition. Okay, I'm done with code now. You can just calm down a bit. And if you have any questions, please jump in. Don't worry about it. Okay, so moving along. We're going to do a test drive. And this test drive is going to be a benchmark. But it's going to be a different benchmark because we don't really care about performance. We can just implement it using C extensions, using C code, C++, whatever. What we want to check is the rate of false positives. That's the metric that really counts in our Bloom filter. So I did a benchmark. I created a Bloom filter. I just put in 1024 bits. I inserted 900 values. And then I tested 248 values. So the Bloom filter is going to have 900 values within it. And we're going to test if we have a lot of false positives with numbers that aren't in the Bloom filter. I ran the benchmark. And the data that really counts is this thing, the number of false positives. And if you remember, we said that the first version, the one that I talked about earlier with a single hash function, it should have a lot more collisions. But the opposite is happening here. And this is really weird because it doesn't make sense. If we want to solve the problem of false positives, we'd add in more hash functions. Well, the fact is that we weren't adding 900 entries in the second version. We were adding 270 because I was hashing it 3 times. So the Bloom filter was filling up really quickly, and the chance for collisions is a lot higher. I did a second benchmark, and I just changed that value, the inserted values. It went from 900 to 300, and in the second version, it's going to insert actually 900 values, so it's not going to fill in the Bloom filter. And the number of false positives really changed. The first version has a lot more false positives. So, where do I want to go with this? Well, the expected amount of entries is going to influence the performance. If you're getting a lot of false positives, you're going to end up making a lot of extra requests to your server or whatever is the application you're using. And the Bloom filter size is going to be really influenced by this. So you need to estimate the expected amount of entries. The number of hash functions also influences performance, as we just saw. With different numbers of hash functions, we had different numbers of false positives. Luckily for us, this is a solved problem. Getting the optimal size and the optimal number of hash functions is pretty easy. You just run it through a probability function, which I'm not going to show here. And that function depends on the false positive rate. You tell it, hey, I want to have 10% of false positives. And it's going to give you the size and the number of hash functions to achieve that. But it also depends on that expected number of items. And this is not an easy thing. You can't really tell how many times your Bloom filter is going to fill up or anything. So my advice to you would be to benchmark and estimate over and over again, iterate, and find the best option that suits your needs. It's really a case-by-case basis. Okay, so I'm almost done. I'm just going to tell you a bit about what we encounter in the wild, how our company is using Bloom filters, because it's not just in browsers, and we're going to get to that in a bit. Okay, so let's start with Medium. I'm pretty sure most of you have heard of Medium by now, especially since the Pixel Scamp blog is hosted there. They have this really cool use of Bloom filters, since you can get suggested articles that suit your own personal tastes. But they had a problem, which was, how do I avoid giving a duplicate entry to a user? How do I avoid suggesting an article that a user has already read? So instead of going through the database and just keeping there all the values, all the posts that a user has read, which would pile up really quickly and blow up with their whole storage, they just put everything in a Bloom filter. And it's really small. I don't have any numbers for that, but there's a blog post about it on the Medium blog. You should check it. And that basically saves them a lot of computation power and a lot of memory. Google Chrome actually uses Bloom filters. So the thing we implemented a while ago is actually within Chrome. And there's also a blog post about it. And it's about 18 megabytes. It has about 18 megabytes. And there's an estimate that it has 1 million malicious URLs within it. And that's going to end up being really huge in a database. But it's 18 megabytes. And today's age, it's basically nothing. So one of the companies that uses Bloom filters in a very creative way is Facebook. They had this issue where, so everyone needs to be connected, and I want to search for someone, but I want to search for my friends first because there's a whole context around myself. And how do they force the search to show up friends first? Well, every time you hit the search bar, they're going to load up the social graph, and that's the graph of your friends, and each node is connected to a list of names. If you typed F, it would go through the graph and pick up all of the friends that started with F in the first name or in the last name. But this is basically just brute forcing it. So they would iterate over a social graph, and they would compute a lot. They're also using pointers, so they wouldn't be using the CPU cache, and it was really troublesome. The search bar was really slow. What they did was adding a Bloom filter. And the Bloom filter contained the first letter of the first and last name. So they would simply, it's a simple hash calculation, they would check it, and if the Bloom filter returned a positive value, then they would brute force it the same way as before, but now they're clearing up a lot of negative values, so it really worked for them. And this was in production like 6 years ago or something. There's a whole talk about it. Well, this is supposed to be Internet of Things. I'm working with IoT devices right now, and each device has different resources. Each device is connected to a different sensor. And IoT devices have very limited resources when it comes to computing and memory. So my first alternative to know which node to contact, say if I want to get the temperature reading, I have to contact a node which has a temperature sensor. And the first alternative was keeping a list within each node saying what resources do the other nodes have. But that was using up a lot of memory. So I switched to communications. I would ask node, hey, do you have this resource? Do you have that resource? And so on. And that introduced both a lot of computation power and it slowed down the whole thing. So I started digging into Bloom filters, and now each node has a Bloom filter with all the resources that the other nodes have. And if I get a positive, I'm going to ask for that resource. If it doesn't have, it's a false positive, but I can deal with that. It's just one round trip. So it's pretty good. Before I get this over with, I just want to say one last thing that I haven't mentioned, which is that you can't remove elements from Bloom filters. Once it's in there, it's not going to come out because you would mess up the whole false positive thing. So if your application really needs to remove elements from Bloom filters, don't worry. There are a few alternatives from which you can choose from, and that's going to end up any moment. OK, here we go. And yeah, this is all I got. Thank you for being here. And if you have any questions, feel free to ask. If you want stickers, we have stickers as well. Thank you.